first chapter we are going to talk in this semester is correlation and simple linear regression. So we are going to explain two types in chapter 12. One is called correlation, and the other type is simple linear regression. Maybe this chapter will, I'm going to spend about 2 lectures in order to cover these objectives. The first objective is to calculate the coefficient of correlation. Second objective, the meaning of the regression coefficients, beta B0 and beta 1. And the last objective is how to use regression analysis to predict the value of dependent variable based on an independent variable. It looks like that we have discussed objective number 1 in chapter 3. So calculation of the correlation coefficient is done in chapter 3, but here we'll give some details about correlation also. A scatter plot can be used to show the relationship between 2 variables. For example, imagine that we have a random sample of 10 children, and we have data on their weights and ages. And we are interested to examine the relationship between weights and age. For example, suppose child number 1 his or her age is 2 years with weight, for example, 8 kilograms. The other child, his weight or her weight is 4 years, and his or her weight is, for example, 15 kilograms, and so on. And again, we are interested to examine the relationship between age and weight. Maybe there exists sometimes a positive relationship between the 2 variables. That means if one variable increases, the other one also increases. If one variable decreases, the other will also decrease. So they have the same direction, either up or down. So we have to know, number 1, the form of the relationship. This form could be linear. Here we'll focus just on linear relationship between x and y. The second, we have to know the direction of the relationship. This direction might be positive or negative relationship. In addition to that, we have to know the strength of the relationship between the 2 variables of interest. The strength can be classified into 3 categories: either strong, moderate, or there exists a weak relationship. So it could be positive strong, positive moderate, or positive weak, the same for negative. So by using scatter plot, we can determine the form, either linear or non-linear, but here we are focusing on just linear relationship. Also, we can determine the direction of the relationship. We can say there exists positive or negative based on the scatter plot. Also, we can know the strength of the relationship, either strong, moderate, or weak. For example, suppose we have, again, weights and ages. And we know that there are 2 types of variables in this case. One is called dependent, and the other is independent. So we, as we explained before, is the dependent variable, and age is independent. Always, a dependent variable is denoted by y, and always on the vertical axis. So here we have weight, and independent variable is denoted by x, and x is in the x-axis or horizontal axis. Now scatter plot, for example, here, child with age 2 years, his weight is 8. So 2 years, for example, this is 8. So this star represents the first pair of observation, age of 2 and weight of 8. The other child, his age is 4 years, and the corresponding weight is 15. For example, this value is 15. The same for the other points. Here we can know the direction. In this case, there exists positive. Form is linear. Strong or weak or moderate, it depends on how these values are close to the straight line. Closer, it means stronger. So if the points are closer to the straight line, it means there exists stronger relationship between the two variables. So closer, it means stronger, either positive or negative. In this case, there exists positive. Now, for the negative association or relationship, we have the other direction. It could be this one. So in this case, there exists linear but negative relationship, and this negative could be positive or negative. It depends on the points. So it's positive relationship. The other direction is negative. So the points, if the points are close, then we can say there exists strong negative relationship. So by using scatter plot, we can determine all of these for direction and strength. Now here the two variables we are talking about are numerical variables. So the two variables here are numerical variables. So we are talking about quantitative variables. But if you remember in chapter 11, we talked about the relationship between two qualitative variables. So we use chi-square test. Here we are talking about something different. We are talking about numerical variables. So we can use scatter plot. Number one. Next, correlation analysis is used to measure the strength of the association between two variables. And here again, we are just talking about linear relationship. So this chapter just covers the linear relationship between the two variables, because sometimes there exists non-linear relationship between the two variables. So correlation is only concerned with the strength of the relationship. No causal effect is implied with correlation. We just say that X affects Y, or X explains the variation in Y. Scatter plots were first presented in chapter 2, and we skipped, if you remember, chapter 2. And it's easy to make scatter plots for Y versus X. In chapter 3, we talked about correlation. So correlation was first presented in chapter 3. But here I will give just a review for computation about correlation coefficient or coefficient of correlation. First, coefficient of correlation measures the relative strength of the linear relationship between two numerical variables. So here we are talking about numerical variables. Sample correlation coefficient is given by this equation, which is sum of the product of xi minus x bar, yi minus y bar, divided by n minus 1 times standard deviation of x times standard deviation of y. We know that x bar and y bar are the means of x and y respectively, and sx, sy are the standard deviations of x and y values. And we know this equation before. But there is another equation. That one can be used for computation, which is called shortcut formula, which is just sum of xy minus n times x bar y bar divided by square root of this quantity. And we know this equation from chapter 3. Now again, x bar and y bar are the means. Now the question is, do outliers affect the correlation? For sure, yes. Because this formula actually based on the means and the standard deviations, and these two measures are affected by outliers. So since R is a function of these two statistics, the means and standard deviations, then outliers will affect the value of the correlation coefficient. Some features about the coefficient of correlation. Here, rho is the population coefficient of correlation, and R is the sample coefficient of correlation. Either rho or R have the following features. Number one, unity free. It means R has no units. For example, here we are talking about weights, and weight in kilograms, ages in years. And for example, suppose the correlation between these two variables is 0.8. It's unity free, so it's just 0.8. So there is no unit. You cannot say 0.8 kilogram per year or whatever it is. So just 0.8. So the first feature of the correlation coefficient is unity free. Number two, ranges between -1 and +1. So R is always, or rho is always between -1 and +1. So -1 smaller than or equal, R is smaller than or equal to +1. So R is always in this range. So R cannot be smaller than -1 or greater than +1. The closer to -1 or -1, the stronger negative relationship between, or linear relationship between x and y. So for example, if R is -0.85 or R is -0.8. Now, this value is closer to -1 than -0.8. So -85 is stronger than -0.8 because we are looking for closer to -1. -0.8, the value itself is greater than -0.85, but this value is closer to -1 than -0.8. So we can say that this relationship is stronger than the other one. Also, the closer to +1, the stronger the positive linear relationship. Here, suppose R is 0.7 and another R is 0.8. 0.8 is closer to +1 than 0.7, so 0.8 is stronger. This one makes sense. Closer to 0, the weaker relationship between the two variables. For example, suppose R is plus or minus 0.05, for example. This value is very close to 0. It means there exists weak relationship. Sometimes we can say that there exists moderate relationship if R is close to 0.5. So it could be classified into these groups, closer to -1, closer to 1.5, or 0. So we can know the direction by the sign of R. Negative, it means because here R ranges, as we mentioned, between -1 and +1. Here 0. So these values, it means there exists negative. Above 0, all the way up to 1, it means there exists positive relationship between the two variables. So the sign gives the direction of the relationship. The absolute value gives the strength of the relationship between the two variables. So the same as we had discussed before. Now, some types of scatter plots for different types of relationship between the two variables is presented in this slide. For example, if you look carefully at figure 1 here, chart 1, this one, and the other one, in each one, all points are on the straight line, it means there exists perfect. So if the points, if all points fall exactly on the straight line, it means there exists perfect. Here there exists perfect negative. So this perfect negative relationship. The other one perfect positive relationship. In reality, you will never see something like perfect positive or perfect negative. Maybe in real situation. In real situation, most of the time, R is close to 0.9 or 0.85 or something like that, but it's not close, but it's not exactly equal 1. Because equal 1, it means if you know the value of a child age, then you can predict the exact weight. And that never happened. If the data looks like this table, for example, suppose here we have age and weight. Age 1, for example, 3, 5, 7. Weight, for example, 10, 12, 14, 16. In this case, there exists perfect. Because x increases by 2 units, also weights increases by 2 units. Or maybe weights, for example, 9, 12, 15, 18, and so on. So x or age increases by 2 units for each value, for each individual, and also weights are increased by 3 units for each person. In this case, there exists perfect relationship. But that never happened in real life. So perfect means all points are lie on the straight line. Otherwise, if the points are close, then we can say there exists strong. Here, if you look carefully at these points corresponding to this regression line, it looks like not strong because some of the points are not close, so you can say there exists maybe moderate negative relationship. This one, most of the points are scattered away from the straight line, so there exists weak relationship. So by just looking at the scatter plot, sometimes you can. Sometimes it's hard to tell. But most of the time you can tell at least the direction, positive or negative, the form, linear or non-linear, or the strength of the relationship. The last one here. Now x increases, y remain the same. For example, suppose x is 1, y is 10. X increases to 2, y still is 10. So as x increases, y stay in the same position. It means there is no linear relationship between the two variables. So based on the scatter plot, you can have an idea about the relationship between the two variables. Here I will give a simple example in order to determine the correlation coefficient. A real estate agent wishes to examine the relationship between selling price of a home and its size measured in square feet. So in this case, there are two variables of interest. One is called selling price of a home. So we have selling price of a home and its size. Now, selling price in $1,000. And size in feet square. Here we have to distinguish between dependent and independent. So your dependent variable is house price, sometimes called response variable. The independent variable is the size, which is in square feet, sometimes called explanatory variable. So my y is selling price, and size is square feet, or size of the house. In this case, there are 10. The sample size is 10. So the first house with size 1,400 square feet, its selling price is 245 multiplied by 1,000. Because these values are in $1,000. Now, based on this data, you can first plot the scatter plot of house price in y direction, in the vertical direction. So here is house price and size in the x-axis. You will get this scatter plot. Now, the data here is just 10 points, so sometimes it's hard to tell the relationship between the two variables if your data is small. But just this example for illustration. But at least you can determine that there exists linear relationship between the two variables. It is positive. So the form is linear. Direction is positive. Weak or strong or moderate. Sometimes it's not easy to tell if it is strong or moderate. Now, if you look at these points, some of them are close to the straight line and others are away from the straight line. So maybe there exists moderate, for example, but you cannot say strong. Here, strong, it means the points are close to the straight line. So sometimes it's hard to tell the strength of the relationship, but you can know the form or the direction. But to measure the exact strength, you have to measure the correlation coefficient, R. Now, by looking at the data, you can compute the sum of x values, y values, sum of x squared, sum of y squared, also sum of xy. Now plug these values into the formula we have for the shortcut formula. You will get R to be 0.76, around 76. So there exists positive, moderate relationship between selling price and a home and its size. So that means if the size increases, the selling price is also increases. So there exists positive relationship between the two variables. Any question? Moderate. Strong, it means close to 1, 0.8, 0.85, 0.9, you can say there exists strong. But here it's not a strong relationship, you can say it's moderate relationship. Because it's close, if you just compare this value and other data gives 90%. Other one gives 85%. So these values are much closer to 1 than 0.7, but still this value is considered to be high. Any question? Next, I will give some introduction to regression analysis. First, regression analysis used to, number one, predict the value of a dependent variable based on the value of at least one independent variable. So by using the data we have for selling price of a home and size, you can predict the selling price by knowing the value of its size. So suppose, for example, you know that the size of a house is 1,450 square feet. What do you predict its size, its
Price.
sale or price? So by using this value, we can predict the selling price. Next, explain the impact of changes in independent variable on the dependent variable. You can say, for example, 90% of the variability in the dependent variable in selling price is explained by its size. So we can predict the value of the dependent variable based on a value of one independent variable at least, or also explain the impact of changes in independent variable on the dependent variable. Sometimes there exists more than one independent variable. For example, maybe there are more than one variable that affect the price, selling price. For example, beside selling price, beside size, maybe location. Maybe location is also another factor that affects the selling price. So in this case, there are two variables. If there exists more than one variable, in this case we have something called multiple linear regression. Here we just talk about one independent variable. There is only, in this chapter, there is only one x. So it's called simple linear regression. The calculations for multiple takes time, so we are going just to cover one independent variable. But if there exists more than one, in this case you have to use some statistical software as SPSS, because in that case you can just select a regression analysis from SPSS, then you can run the multiple regression without doing any computations. But here we just covered one independent variable. In this case, it's called simple linear regression. Again, the dependent variable is the variable we wish to predict or explain, the same as weight. Independent variable, the variable used to predict or explain the dependent variable. For simple linear regression model, there is only one independent variable. Another example for simple linear regression, suppose we are talking about your scores. Scores is the dependent variable, can be affected by number of hours. Hours study, or studying hours, number of studying hours. Maybe as number of studying hours increases, your scores also increase. In this case, if there is only one x, one independent variable, is called simple linear regression. Maybe another variable, number of missing classes or attendance. As number of missing classes increases, your score goes down. That means there exists negative relationship between missing classes and your score. So sometimes maybe there exists positive or negative. It depends on the variable itself. In this case, if there are more than one variable, then we are talking about multiple linear regression model. But here we have only one independent variable. In addition to that, a relationship between x and y is described by a linear function. So there exists a straight line between the two variables. Changes in y are assumed to be related to changes in x only. So any change in y is related only to the changes in x. So that's the simple case we have for regression, that we have only one independent variable. Types of relationships, as we mentioned, maybe there exist linear it means there exists straight line between x and y, either linear positive or negative, or sometimes there exists non-linear relationship. It's called curved linear relationship. The same as this one, it's a parabola. Now in this case, there is no linear relationship, but there exists curved linear, or something like this one. So these types of non-linear relationship between the two variables. Here we are covering just the linear relationship between the two variables. So based on the scatter plot, you can determine the direction, the form, the strength. Here, the form we are talking about is just linear. Now, another types of relationship, the strength of the relationship. Here, the points, either for this graph or the other one, these points are close to the straight line. It means there exists strong positive relationship or strong negative relationship. So it depends on the direction. So strong either positive or strong negative. Here the points are scattered away from the regression line. So you can say there exists weak relationship, either weak positive or weak negative. It depends on the direction of the relationship between the two variables. Sometimes there is no relationship, or actually there is no linear relationship between the two variables. If the points are scattered away from the regression line, I mean you cannot determine if it is positive or negative, then there is no relationship between the two variables. The same as this one. X increases, Y stay nearly in the same position, then there exists no relationship between the two variables. So, a relationship could be linear or curved linear. It could be positive or negative, strong or weak, or sometimes there is no relationship between the two variables. Now the question is, how can we write, or how can we find the best regression line that fits the data you have? We know the regression is the straight line equation is given by this one. Y equals beta 0 plus beta 1x plus epsilon. This term pronounced as epsilon. It's a Greek letter, the same as alpha, beta, mu, sigma, and so on. So it's epsilon. I, it means observation number I. I 1, 2, 3 up to 10, for example, is the same for selling price of a home. So I 1, 2, 3 all the way up to the sample size. Now, Y is your dependent variable. Beta 0 is population y-intercept. For example, if we have this scatter now. Now, beta 0 is this one. So this is your beta 0. So this segment is beta 0. It could be above the x-axis, I mean beta 0. Could be positive, might be negative. Now this beta 0 fall below the x-axis, so beta 0 could be negative. Or maybe the straight line passes through the origin point. So in this case, beta 0 equals 0. So it could be positive, negative, or equal 0, but still we have positive relationship. That means the value of beta 0, the sign of beta 0, does not affect the relationship between y and x. Because here, in the three cases, there exists positive relationship, but beta 0 could be positive or negative or equal 0, but still we have positive relationship. I mean, you cannot determine by looking at beta 0, you cannot determine if there exists positive or negative relationship. The other term is beta 1. Beta 1 is the population slope coefficient. Now, the sign of the slope determines the direction of the relationship. That means if the slope has positive sign, it means there exists positive relationship. Otherwise, if it is negative, then there is negative relationship between the two variables. So the sign of the slope determines the direction. But the sign of beta 0 has no meaning about the relationship between y and x. X is your independent variable. Epsilon I is the random error term. Because here if we are talking about just size that affect selling price of a home, it means there are some errors you don't know about it because you ignore some other variables that may affect the selling price. Maybe you select a random sample, that sample is small. Maybe there is there is sampling error. So all of these are called random error terms. So all of them are in this term. So epsilon I means something you don't include in your regression modeling. For example, you don't include all the independent variables that affect y, or your sample size is not large enough. So all of these measured in random error term. So epsilon I is the random error component. Beta 0 plus beta 1x is called linear component. So that's the simple linear regression model. Now, the data you have, the blue circles represent the observed value. So these blue circles are the observed values. So we have observed y, observed value of y for each value of x. The regression line is the red one is called the predicted values. Predicted y. Predicted y is denoted always by y hat. Now the difference between y and y hat is called the error term. So epsilon I is actually the difference between the observed value and its predicted value. Now, the predicted value can be determined by using the regression line. So this line is the predicted value of y for xi. Again, beta 0 is the intercept. As we mentioned before, it could be positive or negative or even equal 0. The slope is a change in y divided by a change in x. So these are the components for the simple linear regression model. Y again represents the dependent variable. Beta 0 y-intercept. Beta 1 is your slope, and the slope determines the direction of the relationship. X independent variable epsilon I is the random error term. Any question? The relations may be positive or negative. It could be negative. Now, for negative relationship, beta 0 could be positive or negative, where beta 0 is negative, beta 0 equals 0. So here there exists negative relationship, but beta 0 may be positive or negative or equal 0. So again, the sign of beta 0 also does not affect the relationship between the two variables. Now, we don't actually know the values of beta 0 and beta 1. We are going to estimate these values from the sample we have. So the simple linear regression equation provides an estimate of the population regression line. So here we have yi hat is the estimated or predicted y value for observation I. The estimate of the regression intercept P0. The estimate of the regression slope is B1, and this is your x or independent variable. So here is the regression equation. Simple linear regression equation is given by y hat, the predicted value of y, equals b0 plus b1 times x1. Now these coefficients, b0 and b1, can be computed by the following equations. So the regression equation is given by y hat equal b0 plus b1x. Now the slope b1 is r times standard deviation of y times standard deviation of x. This is the simplest equation to determine the value of the slope. b1r, r is the correlation coefficient. sy is x are the standard deviations of y and x, where b0, which is y-intercept, is y bar minus bx bar, or b1 x bar. Sx, as we know, is sum of x minus x bar squared divided by n minus 1 under square root, similarly for y values. So this, how can we, these formulas to compute the values of b0 and b1. So we are going to use these equations in order to determine the values of b0 and b1. Now, what's your interpretation about the slope and the intercept? For example, suppose we are talking about your score y and x number of missing classes. And suppose, for example, y hat equal 95 minus 5x. Now let's see what's the interpretation of b0. This is b0. So b0 is 95. And b1 is 5. Now what's your interpretation about b0 and b1? b0 is the estimated mean value of y when the value of x is 0. That means if the student does not miss any class, that means x equals 0. In this case, we predict or we estimate the mean value of his score or her score is 95. So 95, it means when x is 0, if x is 0, then we expect his or her score is 95. So that means b0 is the estimated mean value of y when the value of x is 0. Now what's the meaning of the slope? The slope in this case is negative 5. b1, which is the slope, is the estimated change in the mean of y as a result of a 1 unit change in x. For example, let's compute y for different values of x. Suppose x is 1. Now we predict his score to be 95 minus 5 times 1, which is 90. When x is 2, for example, y hat is 95 minus 5 times 2, so that's 85. So for each 1 unit, there is a drop by 5 units in his score. That means if number of missing classes increases by 1 unit, then his or her weight is expected to be reduced by 5 units because the sign is negative. Another example. Suppose, again, we are interested in weights and ages. And imagine that just for example, y hat equal 3 plus 4x. Now, y hat equal 3 if x equals 0. That has no meaning because you cannot say age of 0. So sometimes the meaning of y-intercept does not make sense because you cannot say x equals 0. Now for the slope of 4, that means as his or her weight increases by 1 year, then we expect his weight to increase by 4 kilos. So as 1 unit increase in x, his weight is expected to increase by 4 units. So again, sometimes we can interpret the y-intercept, but in some cases it has no meaning. Now for the previous example, for the selling price of a home and its size, B1 R is y divided by Sx. R is computed. R is found to be 76%, Sy divided by Sx. That will give 0.109. B0 y bar minus B1 x bar. B0 equal y bar for this data is 286 minus B1. So we have to compute first B1 because we use it in order to determine B0. And calculation gives 98. So that means, based on these equations, y hat equals 0.10977 plus 98.248 times x. X is the size. 0.1 is this. B1 is 0.1, B0 is 98, so 98.248 plus B1 times x. So this is your regression equation. So again, the intercept is 98. So this amount, this segment is 98. Now the slope is 0.109. So house price, the expected value of house price equals B0 98 plus 0.109 square feet. So that's the prediction line for the house price. So again, house price equal B0 98 plus 0.10977 times square root. Now what's your interpretation about B0 and B1? B0 is the estimated mean value of y when the value of x is 0. So if x is 0 in this range of observed x values and never you have a home or a house of size 0, so that means this value has no meaning. Because a house cannot have a square footage of 0. So B0 has no practical application in this case. So sometimes it makes sense. In other cases, it doesn't have that. So for this specific example, B0 has no practical application in this case. But B1, which is 0.1097, B1 estimates the change in the mean value of y as a result of 1 unit increase in x. So for this value, which is 0.109, it means this value tells us that the mean value of a house increased by this amount, increased by 0.1097, but we have to multiply this value by 1,000 because the data was in $1,000, so around 109, on average for each additional 1 square foot of a size. So that means if house size increased by 1 square foot, then the price increased by around $109. So for each 1 unit increased in the size, the selling price of a home increased by 109. So that means if the size increased by 10 square foot, it means the selling price increased by 1,097.7. Make sense? So for each 1 unit increase in its size, the house selling price increased by 109. So we have to multiply this value by the unit we have, because y was in $1,000. Here, if you go back to the previous data we have, the data was house price was in $1,000, so we have to multiply the slope by 1,000. Any question? Now we can use also the regression equation line to make some prediction. For example, we can predict the price of a house with 2,000 square feet. You just plug this value. So we have 98.25 plus 0.109 times 2,000. That will give the house price for 2,000 square feet. So that means the predicted price for a house with 2,000 square feet is this amount multiplied by 1,000. So that will give $317,850. So that's how can we make predictions for y, for house price at any given value of its size. So for this data, we have a house with 2,000 square feet. So we predict its price to be around 317,850. I will stop at coefficient of correlation. I will stop at coefficient of determination for next time. That's all.